In elementary physics, you're used to forces causing an object to accelerate and gain kinetic energy, like the whole body accelerating and gaining speed, gaining kinetic energy. But isn't it also possible for these forces to squeeze the object or extend the object? And what effect would that have on the energy? The answer is here. Let's focus on an ideal gas and look at the piston applying a force to the gas as it moves inwards. The piston hits the particles like a bat hitting a ball. And when a bat hits a ball, the ball gains kinetic energy. So we see that if you compress a gas, that is, you have a force doing work upon the gas, that work can increase the kinetic energy of the object, but the kinetic energy of its internal parts. We call that increasing the internal energy of the object, different from the whole object in motion. And this is just the internal energy that's going up. Notice that when the piston compresses the gas, their speed increases, and they lose speed as the piston goes out. When the piston goes out, they lose speed. That's like bunting a baseball. When you bunt the ball, you move back against the motion of the ball and it slows the ball down. So we see that either way, on the way in, energy goes up. On the way out, the energy goes down. This is what the first law of thermodynamics is all about. The first law of thermodynamics says that there are two ways to change the internal energy of an object. Mainly, we'll be focusing on ideal gases. But in general, there are two ways to increase that internal energy. Number one, you could put heat into the object. Heat. So that's the first one. The second way to increase the internal energy is to do work upon it. So we need to remember exactly what Q represents. Q is the quantity of heat input to the object. We should remember the different forms of heat. There's conduction, convection, and radiation. Mainly, we'll be discussing radiation. It's the only form of heat that we'll discuss in detail. So the heat of a fire, you can feel the heat of a fire through a vacuum. Think of the sun. You can feel the heat of the sun through the vacuum of space. That's radiation. So you can increase the energy of a thing, of course, by using heat. That's one way to do it. Now, notice that Q represents the heat input to the system. Of course, Q can also be negative if it leaves the system. Okay, so the default sign for it is positive for heat coming in. W represents work done on the system. In other words, it's positive for energy input. That's when the gas is squeezed by the piston. The energy goes up. But of course, when the piston recedes and the gas pushes the piston outwards, then the gas is giving up energy, and we would say the work done on it is then negative. It's helpful to put down those signs in this case. Positive, there's an energy input. Negative for output. For example, when the gas expands. From an engineering point of view, that's the one we care about, is actually the negative one, because we'd like the gas to give us some of its energy to make a car go. So we want to know how much energy the gas can give us by doing work. We'd like to let the pressure of the gas push a piston outwards. The piston, through some means, is connected to the drive shaft of a car and makes the car go. So first, let's figure out how much work the gas pressure gives out. In other words, how much work you get from the gas. And we'll call that W prime. The pressure of the gas, it always pushes outwards. And suppose that it pushes the piston to the right through some distance dx. We can figure out how much work you get out from the engine by taking the integral of f dx, where f is the pressure force from the gas. We have to integrate because as the piston goes out, the gas might lose pressure. And so the force changes with x, and you have to actually do an integral to account for it. So I'd rather write this in terms of pressure instead, and that's easy. Force is pressure times area. That's the area of the piston. So I have pressure times area times dx. But what's area times dx? It's nothing but the volume that the piston moves through. In other words, the extra volume that is gained by the gas. So force is pressure times area. Area times dx is the change in volume. So this is the same thing as pressure times the change in volume of the gas. Actually, this is only approximately true because if there's any kind of friction in any part of the piston, then the work you get out of the engine will be a little bit less than that. But we're going to assume an ideal situation. So that's the work you get from the engine. In my picture, I imagine the dx was to the right. Of course, you can also turn the gears backwards and you can compress the gas. In that case, dx is negative and dv is negative. It's losing volume in that case. So W prime can be a positive number if the gas expands, and it can be a negative number if the gas is being compressed. Sometimes we'd rather discuss the work input. In fact, that's how we set up the first law. The first law was written as saying that you can change the energy of a system by putting heat into it or doing work upon it, putting work input to the system, like compressing it. The work input, W, is just opposite to the work from the engine. They're just opposite in sign. In other words, it's minus the integral of PdV. That's easy to understand. If the gas gives out 1,000 joules to make the car go, then the work input to the engine is negative 1,000. The gas is actually losing energy. The internal energy is dropping by 1,000 due to the output of energy. So depending on which textbook you use, our textbook uses the work input, W is minus PdV. And then other textbooks that you might encounter later on will use W prime instead. However, either way, whichever choice you make, the first law always looks like this. The heat input minus integral PdV. Whether you want to talk about W, if you use W prime, then it's Q minus W prime. And if you use W, then it's Q plus W. Either way, it's always minus integral PdV. Okay, so what this is telling us is we can figure out how much work the gas gives out by expanding by doing an integral of the pressure with respect to volume. It means that PV diagrams are going to be extremely important in this subject. It means basically by looking at a graph of pressure versus volume, we can figure out how much work the gas has done in going from one state, So this is high pressure, low volume. That's a very squeezed gas. And the gas somehow expands to a low pressure, for example. So it goes from one state to another. How it goes from A to B depends on the circumstances. Um, you could pour a lot of heat into the gas as it expands, and that would help it maintain a high pressure. Or you could allow no heat to enter the gas at all, and the gas will get cold as it expands, like a can of air. When you blow the air out of the can gets super cold. So how it goes from A to B can be different. But the point is that to figure out the amount of work that is done, you have to do an integral of PdV. So we always need to look then at the area under the graph. That area tells us how much work the gas has done for us. Now, the integral of PdV is W prime. The integral of minus PdV, the minus in front of it, gives us the work uh, done on the gas. Remember, there are different signs. Work from the gas, what I call W prime, versus the work input to the gas. Our textbook will always use W, the work input, minus the integral PdV. If I want a gas to go from state 1 to state 2, I can't just ask it nicely. We have to take the gas through a series of steps to make it happen. Depending what choices you make, you could either get a lot of work out of the gas or only a little bit. Let's look at these two examples, A and B, where we let the gas evolve from state 1 to 2, but in two very different ways. We want to understand intuitively, in very simple terms, how you make a gas do that, to go from one state to another. All we have is a piston filled with air, a burner, some ice, and a set of weights. Ultimately, we want to lift the weights, basically, so that the gas is doing work for us. How do we do that? Okay, well, we start with the gas. It's just at normal atmospheric pressure to begin with, P0. But then I pile weights on it so I get into state 1, which is double atmospheric pressure. So I'd put a bunch of weights on top of the piston, like a stack of weights. Now the gas is compressed in there to 2P0. That's just our starting condition. High pressure gas in a small volume. Let's look at picture A first. I want to make the gas lower its pressure, but keep the same volume. It's easy to lower the pressure of the gas because you see the gas pressure, as we've seen in many examples, the gas pressure is just determined by how much weight's pushing externally upon it. So I can easily lower the pressure of the gas. I just have to take weights off. What's trickier is how do I maintain the volume of the gas while I take the pressure off? To maintain the volume, you see the tendency is if I take weights off, the gas piston is going to rise. But it will not rise if I extract heat out from the gas. In other words, I ice it down. So to go along this vertical leg, I have to ice down the gas. That means you remove heat out of it. You ice it down while you remove weight. Okay, then we've gotten now here to atmospheric pressure and same volume though. Now, how do I make the gas expand to twice the volume while maintaining the pressure? Can't ask it nicely, I have to do something to make it happen. To keep the pressure the same, that's easy. Just don't add any weight to the piston anymore. To make it expand, I'll have to input heat. If I put heat into the system, then I can make the gas, expand outwards. So that'll take an input of heat. In other words, use the burner on that stage. Notice also, as it goes from V naught to 2 V naught, it's doing work. It is lifting the weight of the piston from one height to a greater height. So we see how, through practical means, we can make the gas evolve from one state to another. Let's compare it against option B. In option B, I keep the gas at a high pressure first and make it expand to twice the volume. How do I do that? Well, again, just put the burner. Don't change any of the weights. You got all the weights piled on it. Don't change that. That'll keep the pressure the same. You just put the burner on it. That will drive the piston upwards and lift the weights. Then I want the gas to drop in pressure back to atmospheric pressure. And again, I do that with ice. I take heat out, put ice all around it, and then I remove the weights. Hopefully that gives some simple intuition about how you make the gas do these things. You draw heat out of it, you put heat in it, and so on. Add weights, remove weights. Important question, how would you physically know the work is different along the different paths, A versus B? Mathematically, I can tell because look, A has a tiny area. Remember, the work is minus the integral of PdV. So I can tell that the work the gas is giving is very small in option A because the area is very little compared to option B, has this big rectangle. That's how you mathematically know the work is different. How would you physically, intuitively know, how could a child know that option B gives way more work than option A? The answer is, in option B, wasn't the gas expanding with all these weights on top of it? And aren't you doing more work if you're lifting more weights? Sure. Option A, you took the weights off and then it expanded. It means it was only lifting the piston alone, hardly any weight at all. How does an engine work? Air is the substance which makes the engine go. Gas, what I mean is gasoline provides the heat. The actual substance which drives the car is air, nitrogen, oxygen, that's in the cylinder, in this part right here. Now, the spark plug ignites the fuel, the gasoline. That provides heat. The gasoline isn't really the substance that drives the car, it's the heat source. So what happens in the action of the engine is the gasoline burns, provides a whole bunch of heat. The heat gives work and pushes the piston downwards. Now, then that work that's given out turns the crankshaft. That's what makes the car go. An engine runs on a cycle. It's not enough just to push out once. The crankshaft now has to push the piston back upwards. It does that when the gas in the chamber, in the piston, is cold. So the secret of the engine is you use heat to drive the piston downwards to give work out from the engine. You do have to return a little bit of work, energy, back into the system, but you do that when the air is cold or colder. That way it's easier to squeeze back, and you'll get more work out of the air than you do when you have to squeeze it back to start the cycle over again. So an engine runs on a cycle. It starts with the highly pressurized air, the ideal gas, inside the chamber. It's at a high pressure. It pushes very hard. Heat is provided. The gas, the air, expands, pushing out with a lot of force, turning the crankshaft. Now, it cools off then and drops to low pressure. That's when heat's given out from the engine. And it drops to a lower to a lower pressure. That's when the crankshaft is timed so it pushes it back again when it's low pressure, colder gas, and is able to return it back to its original state. Let's look at some basic facts about an engine process like this. Notice it runs on a cycle. It has to be returning to the original state it started at so it can then push again and keep pushing over and over and over. So a cyclic process starts at some initial state, goes out, and comes back to the same state again. That means that over the whole process, the change in energy is equal to zero. You're just coming back to where you started, no change in the internal energy of the gas, of the air. Okay? Now, since the change of the total energy is zero, that means the amount of Q, the amount of heat that's provided, must just be minus W. It's just conservation of energy. If there's no overall change in energy, Q and W must balance each other. And let me remind you that W, and this is over the entire cycle. So you got to account for all the heat in and out of the gas and all the work that's done over the entire cycle. How do we figure out the work done over the entire cycle? Well, W, remember, is the work. It's like force times distance, which we saw is really minus the integral of PDV. Let's look at how this appears in the PV diagram. You're integrating the pressure with respect to volume, so it's the area under the curve. First, there's the work done on the way out, from here to there. The amount of work that the engine provides would be the full area under the curve. That's the work given by the air in the piston as it pushes the crankshaft outwards. But now remember, the crankshaft now has to give up some of that energy to push the cylinder back to its starting condition. So now you got to integrate back along the lower part of the curve. And you know, when you integrate backwards, that's subtracts off from the area that you had. So integrating back the other way, we just subtract off that lower portion there. And we find that the overall amount of work done in the cycle is just the area enclosed by the cycle. It's just the area inside of the cycle on the PV diagram. Overall, it's going to be a negative number. W represents that area. It's going to be negative, as we discussed, because remember, the meaning of W, the integral, the minus the integral of PDV, is it's the work input to the engine. If the net input is negative 1,000, that's good. That means you're actually getting out 1,000 joules from the engine. So in an engine, when we calculate W, it's going to come out to be a negative number, which is what it's supposed to be. It just sounds weird, but negative 1,000 means the engine's giving out 1,000 joules of work. So the work done in a cycle is just minus the area. That is the area of the PV diagram for the cycle. In this quick example, there are two ways to run the cycle. You can go BC, which is a clockwise cycle, or you could go BA, which is a counterclockwise cycle. Let's calculate the work, the value of W for both different options. Okay, so first, let's go BC. BC is a clockwise cycle. You're compressing the gas when it's cold, and so overall work comes out of the engine. It's easier to squeeze it back. So I'm going to find a negative area. What I'm going to find is W is negative in this case. Okay, so let's do W BC. WBC is going to be minus the area of this triangle, like so. So WBC will be minus 1/2 the area. The base of the triangle is 3 meters cubed. The height of the triangle is 30 pascals. These are both SI units of volume and pressure. So the units for W will come out to be in joules. It comes out to be minus 45 joules. Minus makes sense because along BC, you're going to get a net amount of work out from the engine. What about BA? WBA, that's a counterclockwise cycle. Notice that you're squeezing the gas back when it's highly pressurized. So along B to A, although the geometric area is the same, the amount of work done is going to be positive 45 joules. Meaning the work input to the engine is 45. You have to put work in. There's no overall advantage in going along BA. You got to put work into the engine to make it run along a counterclockwise cycle. Now remember, these values of W that I have here, these are the amounts of work input to the engine. The question actually says, compute the net work done by the gas. So in this case, the work done by the gas would actually be plus 45. In BA, the work done by the gas would be minus 45. So you got to be careful. Our definition of W is it's the work input or the work from the engine, the work from the gas. An engine's driven by the expansion of an ideal gas. The expansion of air is what makes the car go. As we saw before, you can't just ask the gas to expand, you have to control it. It's allowed to expand in a precise, controlled way. So there are different ways to make that happen. 4 main ways to allow a gas to evolve from one state to another. Let's, to get our bearings, let's remind ourselves of this animation. Let's look at the expansion phase here. As the piston goes out, the molecules bounce off of the receding piston and they lose speed when that happens. So on the way out, that's like in baseball, you call it bunting the ball. You move the bat backwards as the ball hits it, and in this case, we see the molecules slow down when that happens. Point is, the tendency of an expansion is to cool off the gas. The gas tends to get cold when it expands. Think of a can of hairspray or compressed air. Doesn't it get super cold when you let the air out? Cold is the result of expansion, generally. However, imagine that you blast a bunch of heat in as the piston goes out. Then you could compensate for the coldness and maintain the temperature of the gas even as it expands outwards. So you're letting it expand, you're easing off on the external pressure and letting the gas expand, but you're blasting heat into it to maintain the temperature. We call that an isothermal expansion. Isothermal meaning maintaining the temperature, same temperature during the expansion. So the definition is delta T is equal to 0, no change in temperature. Let's think in terms of the first law, what this means. If there's no change in temperature of the gas on the way out, that means the molecule's energy hasn't changed, and therefore their internal energy has not changed at all. So it means that the change in internal energy of the molecules of the gas is going to be 0. What does that mean about heat and work? Well, if the change in energy is 0, that means that Q is equal to minus W. Later, we'll calculate the amount of W by integration, and then we'd automatically know the amount of heat needed. Remember, you got to blast heat into the chamber to maintain the temperature. So we can calculate W by integration, and then we automatically know the amount of heat you'd have to put in to make it happen. We'll do those details later. If you don't blast any heat in while it expands, then it's going to get cold as it goes outwards. We call that adiabatic. The definition of it is Q equals 0. The gas is expanding without any heat which enters the chamber. Don't think that means the temperature stays the same, right? If you don't put heat in to compensate, it's going to get super cold as it expands outwards. And that's the result of an adiabatic expansion. Adiabatic expansion means Q is equal to 0. That means the change in energy is just equal to W. Now, when it expands, W is negative, minus 100 joules. That means the gas loses 100 joules as it expands outwards. Losing the change in energy being minus 100 joules means the gas gets that much colder when it expands outwards. Next, an isochoric process. Isochoric means the volume stays the same. Delta V is equal to 0, no change in volume at all. Without any change in volume, the gas isn't doing any work. You're clamping the cylinder in place so it doesn't change its position, volume doesn't change, and then you're putting in heat and energizing the gas without letting it expand. So that means the work is equal to 0, and the change in energy of the gas is just going to be equal to whatever heat you put in with a flame, for example. Isobaric process means you don't let the pressure of the gas change. That means you don't alter the external force that's pushing on the piston. Maintain the pressure on it. In that case, it's going to be expanding. It's just that the pressure is maintained as it expands outwards. Let's look at a drawing of what these look like in a PV diagram. The isobaric one is simple. In a PV diagram, it's just a horizontal line. Delta P is equal to 0 means the pressure stays constant as it evolves from one state to the next. That means the work is very simple to calculate. It's just a rectangle. And I can, in this case, easily say that the work it's the integral minus PdV, which means it's minus that constant pressure multiplied by the change in volume. Isochoric process. That one's easy to draw as well. No change in the volume at all. Means it's just a vertical line in a PV diagram like this. And no work is done. In that case, there's no area to consider. Now let's look at the isothermal process. Isothermal process, there's no change in temperature. That means as it expands from from some small volume to a larger volume, you keep the temperature fixed. What does that mean? And like, what does the diagram look like then? Well, T stays constant. That means P times V stays constant. Remember ideal gas law. If T doesn't change, and of course N is not changing either, if T doesn't change, that means PV equals nRT, means P times V is constant. It means that P, we can write down exactly what it is. It means that P is equal to nRT divided by V. T is constant, so the graph's easy to draw. When you write it this way, it's a graph of 1 over V, which is a hyperbola. Roughly like that. If T is equal to 1,000 Kelvin, then the graph is far away from the origin. If T is equal to 100 Kelvin, then T is small and the graph hugs the axes like this. This is maybe what we call the 1,000 Kelvin isotherm. This is maybe the 100 Kelvin isotherm right here. And it's a hyperbola in the PV diagram. What does an adiabatic process look like? Well, until later, we won't figure out what the exact curve looks like. But what I do know is in an adiabatic process, the gas gets cold. It's going to drop from a high temperature to a low temperature. So I can roughly sketch what it'll look like. Remember, adiabatic, you're not compensating the expansion with any heat. So it gets cold as it expands in that case. And the gas is going to drop from one isotherm to another. So here's 1,000, here's the 100. The gas could expand but lose its temperature as it expands. Precisely what that curve is, we'll learn later. But it must dive down from one isotherm to another during an adiabatic expansion. This is the 1,000, for example, and this is the 100.